Good evening, everyone. So my name is María, and I'm going to present the work that Jan just said. So we've been talking about this in the first session of the workshop, and basically the current pipeline in WoRMS systems, the symbol classification stage usually use, well, right now we are using deep learning model, which to be trained needs a lot of data, and the data consists of the symbol images together with their transcription, and then we just train the network using a scarce function, and then we can use that network to classify new symbols. But this morning, Ichiro especially was discussing that how much money was invested into creating ground truth, and also how much time also was invested into them. So this is, I would say, the main drawback of this current music classification system, that labeling is actually a very tedious task, and we humans are messy and tend to make errors and everything. So we need to invest a lot of time and money into actually creating ground truth to train these networks. Not only this and that, also we have that in cultural heritage, and not only in cultural heritage, like we are seeing that we have so many different notation systems. It's not only modern, but also news and other type of notation systems. Sadly, right now we need a model for each one of them. Like, we don't have a universal model, or if we want to aim to have one, we need to obtain a lot of data for each of those types and then train the model. So it's like the snake that bites its tail. So at this point, what we actually need is learning alternatives that actually use as many as less few level data as possible. And this is what I'm going to introduce today, that we propose a new methodology that try to use as few level data as possible to construct a music symbol classifier. And how did we do that? Basically, we resort to self-supervised learning. That's self-supervised learning, just to give a quick introduction, tries to learn useful representation from completely unlabeled data, and then use those type of representation into one or more downstream class. And in this work, we're going to use it to create a symbol classifier. So the self-supervised learning method that we are using in this work is called variance invariant covariance regularization, or VREG. And I'm going to go over it step by step. So to train, we are going to use this SSL method to pre-train a convolutional neural network that then we are going to use as a symbol classifier. And this pre-training process is going to be as follows. Then it's going to be as, sorry, it's going to be as okay. So we have labeled image bats that is going to go through different distortion processes. Then what we're going to get is two different collections. And we are going to input those two collections into the CNN, and then retrieve those representations and use those representations to compute the loss function. In between the CNN and the loss function computation, we have a network that is called the expander. Basically, what this network that is just span the feature representation space, and in the SSL literature is just used for conversions because it actually helps. But later on, we're going to see that we can actually remove that network. So once that we get those representation, we are going to use the VREG loss function. And this loss function is based on three terms that we are going to go over the three of them. So the first term is called invariance. What this term is going to try to do is that it's going to bring these two representations together into the feature space. Why? Because these two representations actually, can I use the pointer? Sorry. I don't have a mouse. but I when I do that, it actually loses the present. Yeah. Sorry. Okay. So we're going to use the invariance term to actually bring these two representations together in the space because they belong to the same symbol. Then we're going to use another term that is called variance, and this term is going to force the embedding within a band to be different. Why? Because we assume that the image band that we input to the CNN usually contain images that belong to different symbols, and we want this representation to actually be different. And the last term is called the covariance term that actually just what it does is encourage information-rich generation vectors to avoid any trivial solution like producing the same vector for all the symbol or zero vector. So we pre-train the CNN using this reckless function, and you can see that there are some scaling weight for each of the formula terms that are hyperparameters that we will tune in the experiment. So once that we have this pre-trained CNN, at this point we hypothesize that what VREC is trying to do is to create a easy to classify feature space. So we say, okay, if we actually are able to get that representation space, then we can use a representation-based classification method, such as Cannere's neighbor. And moreover, like if this representation space is good enough, then with just a few label samples, then we can get actually pretty good classifier. And if we actually made it work with just 1 to 10 label sample, then we will answer cost effectiveness. So the second stage of our proposal is actually, let's try to do that. We have a query, which is a new image music symbol, and very few label samples, which is actually 1 to 10 few label samples. And we use this pre-trained network that is actually fixed to map the few label data set to the query into the same representation space, and then use the KNN rule to actually classify the query based on the labels of these K nearest neighbors. Okay, so far, so good. But there is a drawback here right now. We're trying to actually use as less labeled data as possible, but how are we training the CNN? We are actually using symbol crops. So to actually obtain those symbol crops, we will have to go back, draw up on the balls and get the symbols, right? There's a huge drawback in this proposal, but we got a solution. We propose crop extraction algorithm that is completely unsupervised, and what we do is that we input a full page image from a music document, and using a sliding window approach, we go through the whole page and retrieve pages like props from this full page, and actually perform a very simple method that is, yes, we convert to grayscale, linearize these drops, and then using the entropy of the image, we decide if the symbol actually if the crop contains a symbol or not. And we use the entropy value is a user-defined threshold, so we can actually fine-tune that threshold to actually put it higher or lower. And these are actually the drops that we recover with this symbol, and then we actually can use this drop to train the whole CNN. So this is the complete overview of this few-salt symbol classification. We use the Captain corpus to test it, to evaluate it. And we actually did much more experiment with other type of manuscript, but they are not music related, so I didn't put them here. But we use the Captain corpus to train its applicability to music symbol classification. And we compare our proposal with 3 different approaches, which is just, let's try to input the flattened images, like there is no feature extraction. Just input these images into the KNN. Another one was using a pre-trained ResNet to compare the proposal with transfer learning, and to use supervised learning using ResNet as the CNN. And we perform bootstrapping to avoid any bias related to the sampling process, and consider only 1 to 10 labeled samples per class. And the result we got, we were very good, especially with just one with just one label symbol. We actually got an improvement of over 80% compared to the baseline strategies. So that is very nice. You can see that the strategies achieve at most 37% of accuracy, and we were able to achieve almost 70%. And if we increase the label sample, then the accuracy actually increased. But there is a point that the supervised framework start to match the performance of the proposal. So it's true that if we keep increasing the symbol per class, then the supervised learning framework is going to be better performing. But we are trying to reduce the label data, so we can say that our proposal is actually aiming to do that. So as a future work, we would like to actually avoid any symbol location labeling, but I think we so far got it with the supervised with the unsupervised drop extraction, but it would be nice to completely remove that, and also to apply to other document analysis tasks. But I'm not going to extend myself a lot in this part because my colleague Paco is going to actually present some work on the out analysis. And this is all, and I hope you enjoy it. So, thank you.